All right, let's take a look at our probability density function here. First, we could check to make sure it's valid. As I said before, the outcomes can actually be larger, our y values can be larger than 1, that's fine. Even though that wouldn't be a valid probability, probabilities in these functions are represented by areas under the curve and have nothing to do with the actual values that the curve or function takes. So this is okay. If we wanted to check, we'd look and make sure everything is above the x-axis, which is true. We don't have anything negative. We don't have to worry about negative probabilities. And we want to verify that our area under the curve is in fact 1. And so if we look here, we can see our x goes from 0 to 1. Our height is 2, so we're doing a triangle. 1/2 base times height is the area for a triangle. Our base was 1, our height was 2. This is definitely 1. We have got our area under the curve is 1. This is a valid probability density function. I do want to take a moment because there is a little bit more going on in this graph to just explain. Our probability density function is this f of x. They also have this capital F of x, which represents the cumulative density function. This is giving you the area under the curve as you sort of go forward in your actual values. So this function would give us actual probabilities, this f of x. And this is, so anyways, we'll see that as we move forward. We kind of get this idea of like area under the curve, and maybe if you've seen calculus, maybe a little bit of sort of an antiderivative feel to it. So we've been asked in this question to find the probability that x is greater than or equal to 0.3. So you might want to look at what that area actually is. So 0.3 is here. We want greater than or equal to that, so our area under the curve is going to be all of this jazz. So if we were to do that, we go, okay, oh, great, another triangle. Let's go ahead and use our triangle formula for our area, 1/2. The base here, we went from 0.3 to 1. So it's just going to be the difference between those two. So 1 minus 0.3 is 0.7. And then our height is still that 2 we saw before. So there's our area under the curve, just a 0.7. Perfection. Now, if I had chosen a different value where we weren't at the actual peak here, it wouldn't have just been that difference, right? Because we wouldn't have gone up to the height of 2. I unfortunately for this problem couldn't really choose anything else because all of the other heights along here don't pass through any of the like obvious values. So it would have been harder for you to find the height. You would have to use like find the actual line. It would have been a problem. But anyways, this is all I really want you to be able to do. Something this simple. And let's just go ahead and verify with that cumulative density function at 0.3 if we were to follow that back over. That's not giving us 0.7, but that's because the cumulative function is only giving left side probabilities. Essentially, that value of 0.3 that we're seeing there is this area, everything adding up from 0, the start of my curve, up until the value that it is at. And so this is another great point. We'll use a lot when we get into the normal distribution, that sometimes it's easier for us to find one side of the curve like this. If we had that cumulative density function, that was all we had, then we would know, okay, well, I actually want greater than that, so I need to do a 1 minus. So that's just another way to have gotten there to what we wanted here, that 0.7. But that's it. That's all we really do with our continuous probability, our continuous random variables, because we can't create these distributions. They have to be given to us unless we're dealing with something like the uniform distribution we saw in that very first example. And we can't, can't really find means and standard deviations, any of that stuff easily, unless, again, we're in that uniform distribution. But again, that's beyond the scope of this class. So for now, this is it, the understanding of this area under the curve and sort of thinking about what that looks like as we move into the normal distribution, which is at the heart of everything we do in this course moving forward.